Hi class, this is Dr. O'Connor here. We're going to talk about chemical reactions, energy rates, and equilibrium in Chapter 7. For this first video, I'm going to talk about energy. We're going to talk about something called entropy, enthalpy, and free energy. So let's go ahead and start. And we're going to discuss both potential energy and kinetic energy. And potential energy is stored energy. And you can think about a rubber band, for example. And let's say you have the rubber band stretched. It now has a lot of potential energy. Now, when I let go of one end of that rubber band, then what's going to happen is the potential energy is going to be converted to kinetic energy, and that is the energy of motion. When we think about attractive forces between ions or atoms, that'd be covalent bonds, these attractive forces between atoms are a form of potential energy. I'm going to cross this part out. I don't like the statement that the energy is stored in bonds because it really isn't. It's a little more complicated than that. In many chemical reactions, the potential energy is converted to heat. So what is heat? Heat is the kinetic energy of the moving particles that make up a compound. So heat is a measure of the kinetic energy. Now, let's go ahead and define stability. And this describes a substance that has little remaining potential energy. So for example, if we take solid sodium and chlorine gas and they combine to form sodium chloride. Now, pure sodium metal is very reactive. If I were to put a drop of water onto pure sodium metal, it will burst into flame. Chlorine gas, and actually this should have a 2 here, chlorine gas is also very reactive, not to mention very toxic. But sodium chloride, we know, it's a very stable substance. I can put a beaker full of sodium chloride on my desk and I can come back in 10 years and it's most likely going to be there. It's very stable. It is not going to revert back to chlorine gas and pure solid sodium metal. So in this case here, our reaction products, so our sodium chloride, has less potential energy than the reactants, the sodium and the chlorine gas. And basically that just means the products are more stable than that of the reactants. So more stable products. Why do some elements react so easily and others do not? Well, whether or not a reaction occurs is going to be dependent on the potential energy contained in the reactants and products. This is where bond dissociation energy comes in. And this is the amount of energy that is required in order to break a bond and separate the atoms in an isolated gaseous molecule. The greater the bond dissociation energy, the stronger the bond. In other words, the more energy it takes to break that bond, the stronger that bond is. Let's take a look at this reaction here. We have diatomic nitrogen, and in order to break this triple bond, remember this has a triple bond between the two nitrogen atoms, it is going to take 226 kilocalories of energy per mole of nitrogen. So we have tables that show us these bond dissociation energies. And we can see right here for a nitrogen triple bond, it's 226 kilocalories per mole. Now, let's take a look at the diatomic chlorine. And diatomic chlorine has one single bond. And if we look this up here for a chlorine-chlorine single bond, it's 58 kilocalories per mole. It would take 58 kilocalories to break the chlorine-chlorine single bond in 1 mole of diatomic chlorine. So obviously this nitrogen-nitrogen triple bond is much stronger than this chlorine-chlorine single bond. And we can tell that from our bond dissociation energies. Now, look at the reverse process here. So let's take a look at the reverse here. We have two nitrogen atoms, and when they come together to form that nitrogen-nitrogen triple bond, then 226 kilocalories of energy are released. So the reverse would be formation of a bond. And when a bond is formed, energy is usually released. When a bond is broken, energy is required. So let's define endothermic and exothermic. An endothermic process is one that absorbs heat and has a positive delta H. We'll talk about this a little bit later. So the bond breaking is an endothermic process. It requires energy. Bond formation, on the other hand, is an exothermic process. This is a process or a reaction that releases heat. The amount of heat or the amount of energy released in forming a bond is numerically equal to the amount of energy absorbed when a bond is broken. So some examples of endothermic and exothermic processes: melting of an ice cube. That requires heat energy. That is endothermic. However, when we take that liquid water and we freeze it, so freezing is the reverse of melting, then we have an exothermic process. The amount of heat transferred in one direction is numerically equal to the amount of heat transferred in the opposite direction. It's only the direction of heat transfer that is different. If it takes X amount of heat to melt a given amount of water, then the same amount of heat will be released when that liquid water is converted to ice. The only difference is one process is endothermic, the other is exothermic. So the law of conservation of energy. Energy can be neither created nor destroyed in any physical or chemical change. So energy is conserved. We're going to look at something called enthalpy, and we represent that with a capital H. And this is a measure of the amount of energy associated with substances that are involved in a reaction, or even a process like melting or freezing. What we measure is the enthalpy change. This delta here, this delta symbol, means change. So the heat of reaction, or the enthalpy change, is the energy of the bonds formed in the product minus the energy of the bonds broken in the reactants. And this is the formula for this here. So what that means is we can determine the heat of reaction, or delta H, for a reaction by using bond dissociation energies. So let's go ahead and take a look at this in more detail. When we have a chemical reaction like we do here, this is a combustion reaction. We're burning methane and oxygen to produce carbon dioxide and water. When the total strength of the bonds in the products is greater than the total strength of bonds broken in the reactants, heat is released. And we have an exothermic reaction. So you can think of heat as being a product. So we can write it either this way, where we have heat as a product, or we write the reaction, and notice here we say delta H is a negative 213 kilocalories per mole. So just by looking at this value here, because it has a negative sign, I know that this is an exothermic reaction. Remember, there's no such thing as a negative energy or a negative heat. The negative sign is used to show that heat is being released. Heat is being released from the system. Turns out that all combustion reactions are exothermic. So we burn a piece of coal, it produces heat. That's exothermic. Now, when the total strength of the bonds formed in the products is less than the total strength of bonds broken in the reactants, then heat is absorbed, and we have an endothermic reaction. In other words, we must put heat into the system in order for the reaction to take place. And in the case of an endothermic reaction then, because we have to add heat, heat can be thought of as a reactant. So we can write the reaction like this, and because heat is on the reactant side, I know this is an endothermic reaction. Or we can write it like this, and we have delta H is equal to a positive 43 kilocalories per mole. This positive sign tells me that this reaction is endothermic. So to summarize, exothermic reactions or processes release heat to the surroundings. Delta H is negative. Endothermic reactions absorb heat from the surroundings. Delta H is positive. The reverse of an endothermic reaction is exothermic. The reverse of an exothermic reaction is endothermic. The numerical value of delta H is equal for both forward and reverse reactions. It's just the sign is opposite. So let's take a look here. We're asked to identify the following as exothermic or endothermic. We already talked about melting an ice cube. It requires heat. So this is endothermic. Boiling of salt water. So when we boil something, we have to put heat in. So that would be endothermic. And freezing, that's just the reverse of melting. We know that melting is endothermic, so freezing is exothermic. Here we're told they want us to estimate delta H in kilocalories per mole for the reaction of hydrogen and nitrogen to produce ammonia. And we need to use the bond dissociation energies. Now what we need the sum of the bond dissociation energies of the reactants, and we're going to subtract from that the bond dissociation energies of the products. Now, before we do this, we need to know what types of bonds are being broken and what types are being formed. So I'm going to go ahead and rewrite this reaction, but I'm going to use Lewis structures. Okay, so this is the nitrogen, and I know hydrogen will have a single bond, and then ammonia, and we know how to draw the structure of that. This allows us to determine the number of bonds that are broken and the number of bonds that are formed. So let's see what we have here. We have one nitrogen-nitrogen triple bond. Okay, oops, we also have to balance this. So what we have here is we have 3 of these, and we put a 2 there. So we have one nitrogen-nitrogen triple bond. We have 3 hydrogen-hydrogen single bonds. Those are broken. And then we have 3 nitrogen-hydrogen bonds, but we have to multiply that by 2. So that's going to be 6 nitrogen-hydrogen bonds that are formed. So let's go ahead and look up what we need. We have 226 kilocalories per mole for the nitrogen-nitrogen triple bond. And we'll add to that the, let's see, hydrogen, that's 103. And we have 3 of those, so 3 times 103 kilocalories per mole. And then what we need to do then is subtract from that the bond dissociation energies of the products. Here we have 6 nitrogen hydrogen bonds that are formed. So let's see, nitrogen hydrogen is right here, and each one is 93 kilocalories per mole. So that'd be 6 times 93, times 93 kilocalories per mole, and I get a negative 23 kilocalories. This would be my delta H. It's equal to a negative 23 kilocalories. So this reaction then would be exothermic. We have a negative delta H. Again, I'll go ahead and balance that for you. That's how you would do any one of these problems. Again, you have to know the types of bonds so you can look them up on the table. And again, we found that the reaction was exothermic. Let's take a look at this problem here. And we're asked in A, is the reaction endothermic or exothermic? Well, for one thing, we see it's a combustion reaction. This is the methane being burned in oxygen to produce carbon dioxide and water. So even without delta H, we would know that this is exothermic. But here we're given delta H, it is negative, so therefore we have an exothermic reaction. So now we're being asked how much heat is released during the combustion of 2 moles of methane. Well, let's take a look at the equation as written. We have a balanced equation here. We have 1 mole of methane reacting with 2 moles of oxygen to produce 1 mole of carbon dioxide and 2 moles of water. So when 1 mole of methane is burned in 2 moles of oxygen, then 213 kilocalories of heat will be released. So if 1 mole of carbon dioxide is produced from this reaction, then 213 kilocalories of energy is released. If 2 moles of water are produced from this reaction, then 213 kilocalories of heat will be released. Now let's say we double the amount of methane as here to 2 moles. Well, that means we would have twice as much heat being produced. So we have 2 moles of methane, and we know from our balanced chemical equation that when 1 mole of methane is burned, 213 kilocalories of heat is released. So what we have is 426 kilocalories of heat is released when we burn 2 moles of methane. Now we're being asked how much heat is released when 3.6 moles of oxygen completely reacts with methane. So we have 3.6 moles of oxygen, and we know from our balanced equation that when 2 moles of oxygen react, 213 kilocalories of heat is produced. So here we have 3.6 times 213 divided by 2, and that's 383 kilocalories released. Let's go to the next problem here. We are asked, is this reaction exothermic or endothermic? We see delta H is positive, so therefore we have an endothermic reaction. Now they want us to write the equation for the reverse reaction and then include heat as a product or reactant. Well, this is an endothermic reaction as written, and we know that the heat would be a reactant, or we can think of it as being a reactant. Let's go ahead and reverse this. I'm going to write it out. So here, our product now becomes our reactant, and then here we have nitrogen and oxygen gas. And remember, in the forward direction, this reaction is endothermic. In the reverse direction, it's going to be exothermic. So in this case here, we would write the heat as a product, okay? Or we would say delta H is a negative 43 kilocalories per mole. Now in this third part, they want to know how much heat is absorbed during the production of 127 grams of nitrogen monoxide by the combination of nitrogen and hydrogen. So we're looking at this reaction here, and so we have 127 grams of nitrogen monoxide. We go ahead and convert that to moles. So 1 mole of nitrogen monoxide is 30.01 grams. And we know from the equation here that, oops, I'm sorry, we need to go up here, that 2 moles, when 2 moles of nitrogen monoxide are produced, we need 43 kilocalories of heat. So we're going to have 127 divided by 30.01 times 43 divided by 2, and that's 91 kilocalories of heat would need to be absorbed. All right, let's talk about a spontaneous process. A spontaneous process or reaction is one that once started will proceed on its own without any external influence. So, for example, gasoline will combine spontaneously with oxygen. A spontaneous process can happen quickly or slowly. Think about rusting of metal. That's slow, but it is spontaneous. The reverse of a spontaneous reaction is a non-spontaneous reaction. So let's take a look at the melting of an ice cube. We know it's endothermic. That means heat is absorbed, and it's spontaneous. And we also note that there's an increase in molecular disorder and randomness because we're going from a solid, and we know that the water molecules are very orderly arranged into a crystal-like structure, and as it melts, the water molecules now are able to slide across one another, so the solid becomes more liquid. So there's an increase in disorder, if you will. Spontaneous signifies nothing about how fast a process occurs. Remember what I said, rusting can take a long time, and it is spontaneous. So for example, a mixture of gasoline and oxygen can remain unreacted for years, or it could ignite instantly when a spark is provided. So that brings us to something called entropy. Entropy is a measure of the amount of molecular disorder in a system. We represent it with a capital S, and its units here are going to be calories per mole times Kelvin. Let's think about this disorder. Again, we have a solid. The particles in a solid are held in a very ordered arrangement. In a liquid, the particles are less ordered. They're still very close together, but they're not as ordered as in a solid. And then in a gas, the particles are able to move randomly about, and they're separated from each other. So what happens is, as we go from solid to liquid to gas, the entropy increases. Also, if we have a reaction like this, and these are gases, okay, so these are gases. Here, on this side of the equation, the reactants, we have 1 plus 3, 4 moles of reactants, 4 moles of gas. Here we only have 2 moles of gas. So when we see a decrease in the number of moles of gas in a chemical reaction, then we see a decrease in entropy. In other words, this is becoming more ordered. What we measure is delta S. That's the entropy change. And it's positive if disorder increases, like the ice cube melting. And it's negative if disorder decreases. So for example, when you have 2 solutions and you mix them together and then a solid forms, that's a decrease in entropy. Things have become more ordered. In general, entropy will increase when solids melt to form liquids, when solids or liquids vaporize to form gases, when solids or liquids dissolve in a solvent to form non-electrolyte solutions, so dissolving alcohol in water or acetone in water, there's an increase in entropy. A chemical reaction, if we're looking at the gases, If there are more gas molecules on the product side, then we have an increase in entropy. So the reverse of the equation we looked at before, here we have 2 moles of gas. Here we have 4 moles of gas. When written this way, there's an increase in entropy. Also, when we heat up a substance, we usually observe an increase in entropy. Things are more disordered. Let's answer some of these questions here. Does entropy increase or decrease in the following processes? Assembling a jigsaw puzzle. Well, before we assemble the puzzle, all the pieces are just randomly arranged. But then when we assemble the jigsaw, they're nicely ordered. They're in a nice arrangement. So in this case, entropy will decrease. There's less disorder. Here we have 3 moles of gas. Here we have 2 moles of gas. We've gone from 3 to 2. So again, there's a decrease in entropy. And then here, formation of a precipitate. Remember, that's a solid when 2 solutions are mixed. That would be an increase in entropy. And here, the evaporation of water. If water evaporates, right, those molecules are going into the gas phase. So this would be an increase in entropy. So take a look at some of those problems in your book that have to do with entropy so you can practice. Okay, one other topic we're going to talk about here is something called free energy change, represented by delta G. And we use this to describe the spontaneity of a process. And these are 2 terms that we need to define. Exergonic, this is a spontaneous reaction or process that releases free energy. It has a negative delta G. An endergonic process is a non-spontaneous reaction or process that absorbs free energy, has a positive delta G. Now remember, when we talk about endothermic and exothermic, we're talking about heat energy. Exergonic and endergonic, that corresponds to free energy and spontaneity. So negative delta G means we have a spontaneous reaction or process. Let me give you an example here. Again, the ice cube that melts. So the ice cube melts, and we know it's spontaneous as long as the temperature is above freezing. Okay, so above freezing. And let's think about the entropy. Now, we're going from solid to liquid. So delta S is increasing. And we also know that delta H is greater than 0 because this is an endothermic process. Okay? So before we do anything, let's take a look at this equation. Delta G is equal to delta H minus T, which is the temperature in Kelvin, delta S. So we know that delta H is the enthalpy change or the heat of reaction, delta S is the entropy change, and the T is the temperature in Kelvin. Now here's how it works. When I say delta H is favorable, what I mean is a delta H that is negative. So an exothermic process. When I say that delta S is favorable, then I mean that delta S is a positive value. In other words, the entropy increases. So an unfavorable delta H would be an endothermic process. It'd be positive. An unfavorable delta S would be a negative or a decrease in entropy. So let's take a look at this. Anytime you have a favorable delta H and a favorable delta S, delta G is always negative. That means that the reaction or process is always spontaneous. So we don't have to worry about temperature. Anytime we have an unfavorable delta H and an unfavorable delta S, then the reaction or process will be non-spontaneous always. And it won't make a difference as far as temperature. Now, here's when temperature makes a difference. When we have a favorable delta H with an unfavorable delta S, then our reaction or process will be spontaneous at low temperatures, but non-spontaneous at high temperatures. When we have an unfavorable delta H and a favorable delta S, then our reaction or process will be non-spontaneous at low temperatures and spontaneous at high temperatures. So back to our ice cube, we know that delta H is positive. We're melting the ice cube, so we have an unfavorable delta H. We know that entropy increases, so that's favorable. So melting of an ice cube is going to be non-spontaneous at low temperatures, and we know at 0 degrees or below, the ice cube's not going to melt, and it's going to be spontaneous at higher temperatures. We know that above 0 degrees or above freezing, that the ice cube will melt. Again, these are the two cases where temperature makes a difference. It's going to affect delta G. Let's take a look at a problem here. We're asked here, is enthalpy favorable or unfavorable? Well, it's negative, so it is favorable. Is the reaction spontaneous at 25 degrees? Well, we're told that delta G is positive at 25 degrees. So it is non-spontaneous. So no, it's not spontaneous. Does entropy increase or decrease? Well, we're not given a value for entropy, but here on this side we have 5 moles of gas. On this side we have 4 moles of gas. So our entropy then, we're going from 5 to 4. That means there's a decrease. So it's unfavorable. So we have an unfavorable delta S. Okay. So in this case, we have a favorable delta H. We have an unfavorable delta S. What that means is this reaction would be spontaneous at lower temperatures. Okay? So make sure you know this chart. All right? This won't be provided on the exam. You have to remember this. Okay, very good. Let's go to next one here. We have another little problem here. And here we're being asked, is the reaction exo or endothermic? We'll take a look here at delta H. It is endothermic. That's positive. What is delta G for the reaction at 27 degrees Celsius? Well, we have to use this equation here. Delta G is equal to delta H minus T delta S. What we need to do is the temperature is in Kelvin. So we need to convert our temperature to Kelvin. So 273 plus 27 is 300 Kelvin. So let's go ahead and write that out. And we're all set to go. So what we're looking for is, we want to find delta G. So delta G is equal to delta H, which is 31.3 kilocalories per mole, minus T delta S, so we have 300 K, and now delta S is in calories per mole, and we need to get that into kilocalories. So 32 calories, we divide that by 1,000 to get kilocalories. That would be 0.032 kilocalories per mole Kelvin. Notice how my Kelvin cancels out here. And let's see what we get. 31.3 minus 300 times 0.032. I get 21.7 kilocalories per mole. That's delta G. So they want to know, is the reaction spontaneous at this temperature? Delta G is positive, so no, it is non-spontaneous. What is delta G for the reaction at 1,000 degrees Celsius? Well, again, delta G is equal to delta H minus T. So the temperature, 1,000 Celsius, is going to be 1,273 Kelvin. Remember, all we do for Kelvin is degrees Celsius plus 273. So that's 1,273 Kelvin. And we have 0.032 kilocalories per mole per Kelvin. Kelvins cancel here. And let's see what we end up with here. 31.3 minus 1273 times 0.032. I get a negative 9.4 kilocalories per mole. And that's my delta G. And is the reaction spontaneous? Yes, delta G is negative. So yes. So in this case here, it was spontaneous at the higher temperature and non-spontaneous at the lower temperature. And we expect that because we have an unfavorable delta H, we have a favorable delta S. So in that case, we're going to have spontaneity at higher temperatures and non-spontaneity at lower temperatures. This is the end of the first video, and I will do the next video. We're going to be talking about kinetics and reaction rates. Everybody have a good day. Bye-bye.